In this video, we want to think more about roots in polynomials, because it actually turns out if you know all the roots, you can create a polynomial's equation from those roots. So I want to remind us of what a root of a function is. A root is a number that when you plug it into x makes the equation equal 0. So if we have something factored like what you see here, keep in mind the roots are just numbers. So this could be something like x minus 3 and x plus 2. So I'm subtracting 3, so 3 is a root. I'm subtracting a negative 2, that's why it's plus, because it's subtracting negative 2. So negative 2 is also a root. But here's what I want you to think about. If we were actually working it out, if we were showing with work that these are the roots, we would say, okay, x minus 3 equals 0, and then I'd solve that by adding 3 to both sides and get that x equals 3. Or if I have x plus 2 equals 0, I would subtract 2 from both sides and get x equals negative 2. That's great. So I have done that to figure out what the roots are. But here's the cool part. Let's say you could see nothing but this. And they told you the roots are x equals 3 and x equals negative 2. And then they said find an equation of a polynomial that has these as its only two roots. Well, we know that this is something, if these are roots, then they make the equation equal 0. So all I have to do to make the equation is get it so this now equals 0 again. In other words, I have an x equals 3 right now, but I want it to be equal 0. So I'll subtract 3 from both sides and get x minus 3 equals 0. And over here I'll add 2 to both sides and get x plus 2 equals 0. So that tells me that I can make an equation of x minus 3 and x plus 2. And that is a polynomial that has the roots of x equals 3 and x equals negative 2. So all I did was work backwards. Now, this isn't of huge importance, perhaps, at this level of math, but I just want you to make sure you're hearing me. I'm just saying this is a polynomial that has these roots. There are other polynomials that have these roots. I could multiply this equation by 2. That's a new equation because I've now multiplied it by 2, but it does still have the same roots we talked about. Or I could multiply it by 3 or 1/2 or pi, whatever, and it would still be a polynomial that has roots of 3 and negative 2. So we are just creating a possible polynomial, one of the possible polynomials that has these roots when we're doing this. So let me show you some more examples of how we're going to do this. Write a polynomial of the least degree with roots 3 and 7. With least degree means we're not going to add on other parts that we don't need to. We're not going to add other possible roots that aren't listed. We're just going to use these two. So same as we said before, we can do x equals 3 and x equals 7 because those are the two roots. I then want to get it so they equal 0 because I know roots are numbers that make it equal 0. So I subtract 3 from both sides and I subtract 7 from both sides. So my polynomial, make sure you do write y equals or f of x equals x minus 3 times x minus 7. Or truthfully, you don't even have to show this work right here if you just remember what I had in the very first slide at the beginning. An equation is just going to be x minus the root. So anytime we're given a root, we just need to write in parentheses x minus the root. So if I do this example just backing up to the beginning, I do y equals, I do a parenthesis, and then x minus the root. First root is 3. Then I do a new set of parentheses, and I do x minus the root, which is 7. And I'm done. So all you have to do to make a polynomial that has these roots is do x minus those roots. Okay, same idea here. Write a polynomial with roots at x equals 2i and x equals negative 2i. Same idea. We are dealing with imaginary numbers right now. So we'll do y equals x minus a root, which will do 2i. It doesn't actually matter which one you do first or second. And then x minus negative 2i. So minus a negative gives me plus 2i. Now these especially, it's not best to leave it this way. We need to go ahead and FOIL this out, because we don't typically write a polynomial with imaginary numbers inside. But if you watch what happens, when we FOIL, we get x squared plus 2ix minus 2ix, and then negative 2i times positive 2i. Negative 2 times positive 2 is negative 4, and I times I is I squared. So you do have to remember what I squared is equal to. Just a reminder, I is equal to the square root of negative 1. So I squared cancels out that square root and leaves us with negative 1. Sorry, I turned that into a t somehow. I squared is equal to negative 1. So we will replace this I squared with negative 1 and get negative 4 times negative 1, which gives me positive 4. And what you also may have noticed is that the terms in the middle will cancel each other out. So we have a positive 2ix minus 2ix, so they cancel, and our final answer then is y is equal to x squared plus 4. That's how we should leave our answer. So do not leave your answer with the imaginaries inside. Even on this first example I did, you could FOIL that out and get another response. You could do x times x is x squared minus 7x minus 3x, and then minus 3 minus 7 multiplied is positive 21. So this would be x squared minus 10x plus 21. In fact, let's just go ahead and make it our habit to FOIL these out. It's a must to do when you have imaginaries, though, like we did on this example. Okay, next up, write a polynomial with roots at x equals negative 5, negative 3i, and positive 3i. Remember, the pattern is to just do x minus the root. I'll do f of x is equal to x minus a negative 5, so that'll be plus 5, x minus negative 3i, that's plus 3i, and then x minus 3i. So I do want to FOIL this out. When you have imaginaries, always do them first, because things will cancel out real nicely when you do that. The middle terms, like they canceled out on that first example, will almost always do that. At least with our level of math, it will. So let's start by FOILing these two over here with the imaginaries. X times x is x squared, x times negative 3i, 3i times x, and then positive 3i times negative 3i. Positive 3 times negative 3 is negative 9, and then I times I is I squared. So we can simplify this. These middle terms cancel out, and remember that I squared is equal to negative 1. So we really have negative 9 times negative 1, which gives you a positive 9. Okay, but sorry, I am missing part of my equation here. It's forgetting the x plus 5 part, because we did now successfully FOIL the imaginary part, but I still need to multiply it out with x plus 5 and x squared plus 9. I just FOIL x times x squared is x cubed, 5 times x squared, and then 9 times x, and then 5 times 9. Sorry, I think my writing is a little bit behind my talking right now. And it almost got all the way up. Maybe I just didn't finish my 5. Let's see. There we go. Okay, so x cubed plus 5x squared plus 9x plus 45 would be our final answer. So just by knowing three roots of negative 5, negative 3i, and positive 3i, we created a polynomial, the equation of a polynomial. We can also relate the number of roots and the type of roots to the degree of our polynomial. The degree is actually equal to the total number of roots in a function, and the total number of complex roots for a polynomial is equal to the number of real roots plus the number of imaginary roots. So I'm going to flip back to an example we already did in here to show you what I mean. On this example, we did this one earlier, we got this as our equation. We can see that it has a degree of 3. It has a degree of 3. And that tells us that there are 3 roots in total. And we can see, if we look back at how we started, there was 1 real root and 2 imaginary roots, and 1 plus 2 does equal 3. We can also use a graph to help us with this, because if we graph this equation, x cubed plus 5x try that again, x cubed plus 5x squared plus 9x plus 45. And we go to the graph. We see it has exactly one x-intercept. And an x-intercept is the same thing as a root or a 0 of the function. So we see just one x-intercept. So that tells us there is one real root, because the imaginary roots don't actually correspond to x-intercepts. Only the real roots do. So the real roots, we can tell how many there are by looking at the number of x-intercepts. So since I can look at this graph and tell there is one x-intercept, it may be a good idea to zoom out just to make sure we're seeing the whole picture. But there is just one x-intercept, so that tells us there's one real root. And since the degree is 3, that must mean there's 3 total. So the degree is 3. That means there's 3 total roots. There's one x-intercept. That tells me there's one real root. So that means there must be 2 imaginary that are left. So let's look at some more examples. Here we go. 9x to the 4th minus 35x squared minus 4. So we want to look at this. I'm going to go back to normal zoom, and we want to see how many roots this has. How many real roots? Okay, so we see, actually let me answer the questions in the order they are here. Getting ahead of myself. We have this equation. It says how many total roots. So I can look right here at the degree. The degree of this function is 4. This polynomial has a degree of 4, so it has 4 total roots. How many real roots? To figure that out, I go and look at the number of x-intercepts. I see 1 on the left, somewhere around negative 2, 1 on the right at around positive 2. So there are 2 x-intercepts. That tells me there are 2 real roots. So again, the number of x-intercepts is the same as the number of real roots. And we know the number of reals plus the number of imaginaries has to equal the total, which is 4. So that means there must be 2 imaginary roots. So the process here is look at the degree. That tells you the total. Look at the number of x-intercepts. That tells you the number of real. And then just do the total minus the real to get the number of imaginaries. So let's try another one like that. 32x cubed minus 32x squared plus 4x minus 4. I go to the graph. And see, I'm getting ahead of myself again. I'm sorry, I just get so excited about the graph. Apparently I'm related to a student of mine named George. Anyway, how many total roots? To figure out the number of total roots, we just need to look at the equation. We don't need the graph for that. We just look at the degree. The largest exponent is 3, so that means there are 3 total roots. Now to figure out the number of real roots, we need to look at the number of x-intercepts. Okay, so we can see here there is one x-intercept. It's right around positive 1. So one x-intercept means one real root. And to get the number of imaginary roots, we just subtract 3 minus 1 and get 2. Just so you know, the number of imaginary roots is always even. They always come in pairs. There could be 2, there could be 4, there could be 6, there could be 8, but it's always an even number because imaginary roots always come in pairs.